So we've seen many examples where we're looking at a confidence interval. I ask you about a specific point, and the point falls inside the interval, and we're having to say something like, "Gosh, at the 95% confidence level, we cannot say, or the mean might be $25, or the average parking time might be more than 10 minutes," and we're not able to give really good answers. And there's been several times where we've really wanted to narrow the interval, make it more accurate. And so it leads to the topic of determining the sample size. And you can see on the screen right now, I have the confidence interval formula for a population mean. And you can see that I have, and let me grab a pen here real fast. Sorry, I should have been ready for this. But you can see I have the X bar value here listed as your point estimate. And so when we take a sample, really, I'm just going to draw a dot because it's a single value. We have absolutely no confidence in that single value until we go around it with what's called the margin of error. And that would be this part here in the confidence interval for a population mean formula. It's a z alpha over 2 times sigma over the square root of n. And really what that's doing is adding some numbers to get to the upper endpoint and subtracting the same amount to get to a lower endpoint. And so what you see on a printout are two numbers, a lower endpoint and an upper endpoint. And this formula is going on behind the scenes. Your software program is doing the math for you, but it's this margin of error that dictates how wide or narrow the confidence interval is. And so if we want to get a smaller or a narrower confidence interval, it's this piece here that we have to play around with. Now, we've seen earlier from discussions that there's two pieces that we really control here. The confidence level, that's the Z value here, we have some control over. Anything between 90 and 99% is appropriate. We know lowering the confidence level will get us a narrower interval. And the sample size, increasing the sample size will get us a narrow interval as well. But what if we want to think about it ahead of time? What if we want to put some thought into it before we create the confidence interval and say, hey, you know what, I'd really like to estimate to within a certain amount. Like I want to estimate the average GPA of students to within 0.1, or I want to estimate the average age of students to within 2 years. There's nothing worse than saying or creating a confidence interval and trying to estimate the average age of students and coming up with something that goes from like 15 to 35, and everyone just shakes their head and says, well, that's not helpful. It's too wide. Well, what if we want to estimate that to within 2 years? Can we do that? And the answer, of course, is yeah. And so what I'm going to do is we're going to specify this margin of error. That's a to within amount. And this is a margin of error here to within amount here. That's a margin of error. And that's a margin of error as well. And so your interval ends up being 2 margin of errors wide. So if you want to estimate the average age of students, if you want the interval to be 4 years wide, the to within amount or the margin of error is going to be 2 years. Does that make sense? Sometimes it's referred to as a half width of the interval. And so what we do is we specify what that margin of error is. We choose this, and then we solve the equation for n. Now, sometimes students are really interested in the algebra, and most times you're not. And so what I'm going to do is I'm just going to show you the results. If you're really interested in seeing how this, when solved for n, becomes this, well, let me know. I'll be glad to show you. Now, in this formula, again, we're choosing the MA, the margin of error. We're going to have to come up with a reliability level. So a 95%, for instance, is going to become a 1.96 number, or a 90% confidence interval becomes a 1.645 number, and 99% becomes a 2.576. Now I'm kind of showing off that I know the table really well, but we've seen how we can find those Z values in the table. And when I do an example, I'll go through that process with you. And I'll show you a little cheat to that too, as a matter of fact. But the bigger issue here is we need an estimate of the variance. We need some estimate of either the variance or the standard deviation to plug in here. Typically, we don't know sigma, so we're having an estimate that comes from someplace. And that's a little bit of a challenge sometimes. Sometimes you can take the range divided by 4 or the range divided by 6 and get an estimate of the standard deviation. And of course, you would square it then and put it into the formula. But in order to solve for n, we're going to need values for each of these things. All right, so here's an example that I want to take a look at. We want to estimate the average textbook cost of students to within $10 at the 95% reliability level. Now, I used to collect information about textbook costs, how much your student's going to spent on textbooks for a semester. And so I have some prior information, and it indicated that the standard deviation is approximately $100. And so based on this information, what size sample should we take? All right, so in order to do this, I need my formula here, and so I need these different pieces. Well, the to within amount, and these questions can be stated a variety of ways, but typically this is the way we're going to do it. The to within amount is the margin of error. Okay, so I'm going to plug that in down there. The standard deviation in this problem, I'm telling you $100, I'm going to plug that in here, and of course I'm going to square it. The toughest piece is always the reliability part. Now, I'd love to say this is a formula that you're not going to have to do, but you are, because most software programs don't offer this. And so I try to make you do the formulas that I have to do. And so we have to be able to convert the 95% or the 90% or the 99% into a z-value. Now, the way I'm going to do it might surprise you. And I guess I should mention, before I go here, let's see if I can take that back. Well, let me go back. No, not going to let me do it. All right, so I should mention, we've seen a confidence interval for a large sample case and a small sample. You notice that I'm using the z in the formula. Typically, when we're asking the question, what size sample should I take, we're assuming that it's going to be a large sample. And so while the ideas still work for small sample stuff, typically we just use the z in the formula. Now you can see I'm putting the t-table up here, and you might be thinking, what the heck? Why are you doing the t-table? Well, bear with me. With a 95% confidence level, what's alpha? Well, our alpha in this case is 5%, right? And you know what we do, or you should know what we do with confidence intervals, is we take alpha over 2 and put that in the tails of the distribution. In this case, it'd be 0.025. So one way of working this and finding the z-value is to put 0.025 in the tail of the z distribution. And then because our z-table works with inside probabilities, we would have to subtract that from 0.5 to get an inside probability of 0.4750 and look that up in the table. Well, it turns out if you were to do that, that inside probability would take you to a z-score of 1.96. But I got a better way for you. The t-table. If I give you values of reliability of 95 or 90 or 99, common values of reliability or confidence, when we look at the t-table comes with columns that work for the most common reliability levels. If you have 95%, our tail probability, the probability out here, is 0.025. Well, we got a column for that. Now, most tables, not the one that I had in PDF form, but most tables here have a little symbol down here that's the infinite sign. And what that means is these are z-values in the table. And so I'm going to come over here and I'm going to grab the 1.960. This bottom row of information in this table are z-values. And so I'm going to take this 1.96 and I'm going to plug it in for the z-value, the 95%. Now, if I had a 90% confidence interval, think what would happen here if this was 90%. Alpha would be 10%, alpha over 2 would be 0.05. Look what value you see here, the 1.645. And there's other columns to this table. There's a 0.01 column that works for 98%. There's a 0.005 column that works with 99%. And so it's a real easy way, it's a kind of a hack to find z-values easily using this t-table. So I thought I'd show that to you, and you'll see it again in another example in a little bit. But now I'm going to plug some numbers in, and hopefully my scribblings don't get in the way. And so I plug the 1.96 number in, square that, divided by the MA, square that, and then the 100 square, and you can see it's 384.16. Now, when it comes to everything you've ever learned about rounding, what have you learned? Let's see, if it's less than 0.5, we round down. If it's more than 0.5, we round up. And so in this case, you'd round down to 384. When it comes to sample sizes, we always round up. And so 385 is the sample size that would be necessary in order to get a margin of error of $10. Okay? So these are formula problems. You're going to find in the homework problems, a lot of these homework problems are really, really good. And you'll realize that after you do a couple of these problems, you got it. watching me do it on the screen and just following along, or how many of you guys are listening to this video right now but also doing something else, which means you're not really listening to the video. It's called multitasking. Multitasking is a way to not do several things well at the same time. So watch what I'm doing here, but then go and practice it. All right, so let's talk about a population proportion. So similar idea. Here's your confidence interval. There's the point estimate, which is the sample proportion, right? That just gives you a value of p hat. That's our one value. We have no confidence in that at all. And then we have our margin of error that goes around. It's the same idea. It's the same story. That's a terrible parenthesis. This is the margin of error. We're going to specify that. But now we're working with the qualitative data again. And so we're talking about estimating the proportion of students that have a tattoo. We want to do that to within 2%. If I tell you, or within 5%, or within 3%, I think is what I use in my example. We want to control how wide our intervals are. That's the whole motivation here. And there's an equivalent formula. It's the same thing. The P and the Q are not squared because they started underneath the square root sign. Now, you need an estimate of P and Q. This is a little tricky now because actually it's a little bit better when it comes to proportions than with the variances that we saw earlier. In order to use the sample size formula for a mean, the one we just did in the example, I need an estimate of the population standard deviation or variance. If I don't have that estimate, I can't use the formula. Whereas here, if in doubt, I can use, I should have put this in the notes, I didn't have to type it out, but I didn't. I can use P and Q equal to 0.5 if no other estimate exists. And I'll just put no other. If no other estimate exists, we can use P and Q equal 0.5. Now I want to try to explain this to you, and I'll show you the implications of it on the example I do in a second. P and Q equal to 0.5, what's that mean? Well, P, remember, we're talking about, we're kind of going back to our binomial days. We're talking about successes and failures. If there's a 50% chance of a success, well, there's a 50% chance of a failure. If there's a 30% chance of success, what's Q then? Well, Q is always 1 minus whatever P is. So if there's a 30% chance of one outcome, there's a 70% chance of the other. And so watch what happens with the math. If I plug in the value of 0.5 for both these guys here, when I multiply those two numbers together, I'm going to get 0.5 times 0.5, 0.25. Okay, I'm just going to scribble over here and write that over here. That's the value when I plug in the P and the Q. What happens if I have a 0.3 for P? Well, as I mentioned, Q is 0.7, so 0.3 times 0.7 is 0.21. Notice it's less than the 0.25. What if P is 0.9? Well, then Q is 0.1. 0.9 times 0.1 is 0.09, much less than the 0.25. Turns out this is the worst case that you can ever run into for sample size purposes. When P and Q are both 0.5, the sample size needs to be as large as it ever would be. As your P gets closer to 0 or 1, when you multiply P times Q, the product of those two things actually is less than 0.25 for any other choice of P and Q. And so we used, if no other estimates exist, we use the 0.5s in here. That way we'll get as big a sample size as we would ever possibly need. In fact, in most cases, it's probably going to be too big. It's bigger than we need, which means our margin of error is going to be less than what we specify it to be. And so we're going to get a more accurate result than what we were hoping for. We're going to get better information. And so by plugging the P and the Q in there, sometimes we call it the conservative estimates of P and Q, because we'll never need a sample size bigger than that. Hopefully that makes sense to you. Again, in the example I do, I'll show you how that plays out, and that may make sense to you. I'll try to go through it so it makes more sense. All right, so when it comes to determining a sample size, what you got to figure out first and foremost is which of those two formulas. The only two we're going to see is one for means, one for proportions. The ones for proportions have P's and Q's in it. The ones for the means have sigmas, actually sigma squared. But so you got to be able to choose the right formula. So here's the example. We want to estimate the proportion of all students who have a tattoo to within 3% at the 90% reliability level. What size sample should we use? So the first thing I got to decide, you can see I have this automatically pop up here, but I got to decide, is that the right formula to use or should I use the other one? What's the key here? Talking about proportions, percentages, rates. Those would be good words to look for. If I talk about means or averages, I'm going to use the other form. So just like we saw in the last example, I got to go through and figure out where all these different pieces go. Now the 3%, that's my to within amount. That's going to show up here as the margin of error. I'm going to put a 0.03 in there. I have to turn the 90% into a z value. Well, we go through this. Oh, look, I got the t table again. Except now my alpha is 10%, my alpha over 2, which is the way the t table works, is 0.05. So I'm going to go down this column. I'm going to go all the way to the bottom, and I'm going to grab the 1.645 number, and that's what I'm going to put in as the z value. Now this is the example where I haven't given you any information, but estimate the proportion of all students who have a tattoo. Now you've heard me talk about this before this semester, and I do have some ideas, but for the purposes of illustration, let's pretend that I don't. Let's pretend this is the first time, or pretend that this is the first time I've ever thought about this idea of students with tattoos, and I'm like, I have no idea. I'm going to put in the value of 0.5 for both. And so it's just a matter of plugging the numbers in and doing some simple math. And because I get 751.7 and round it up to 752, that would be my sample size. Now, you've heard me say on multiple occasions, I believe the true proportion of students with a tattoo is somewhere around 25%. In fact, the sampling that I've done over the years has suggested that it's somewhere between 20 and 30%. I'm not sure where. I don't know. I haven't pinpointed that accurately, but I think it's somewhere between 20 and 30%. Now, going back to the thought of what value should I use for P and Q, if I think the true percentage is somewhere between 0.2 and 0.3, what would you use? Can you see it? I may not have done a good enough job explaining it, but I would like you to be able to reason through it. If I think the true value is somewhere between 20 and 30%, what value should I use in the formula? And here's what I'm going to say. I'm going to use the 0.3. I'm going to put in the 0.3 for P and the 0.7 for Q. Why? Well, here's my choices. If I take the 0.3 and plug it in for P, what's the Q? 0.7, right? When I multiply them, I get a 0.21. Okay? If you say, well, why not use the 0.2? Well, I'd be multiplying that by a 0.8, and I'd get a 0.16. And you're probably thinking, yeah, so what? Well, if I plug the 0.16, if I put those numbers into the formula and use a 0.16, and the proportion really is 20%, I'm fine. I'm really going to be fine. But if the proportion is really 30%, then this number isn't big enough, and my sample size is going to end up too small. And so by using the 0.2 and the 0.8, I would end up with too small a sample size for any value if the proportion is bigger than 0.2. If instead I use the 0.3 and the 0.7 and plug this number in, that's going to work if the true proportion is 30%. And it's actually going to work even better if the proportion is less than 30%, if it's closer to 20% or 25%. My sample size will be too big. I'm going to get more accurate results. I want my margin of error to be 3%, and it would be less than 3% there. And so what if we think the proportion is between 20 and 30%? I'm going to plug in the 0.3, and you can see that my sample size changes. Pretty significant change when you know the value of P, or you think you know the value of P. So in general, how should you approach this? If you're given a range of values and someone says, I think it's somewhere between 60 and 80%, always choose in the sample size formula, always choose the value within the range that's closest to 0.5. So we chose the 0.3 in this case. If I told you the true proportion were somewhere between 60 and 80%, I would choose a 0.6. If someone said, I'm not sure, I think it's somewhere between 40 and 60%, what's the value in there that's closest to 0.5? Well, it would be 0.5 in that case. And so always choose the value from that range that's closest to the 0.5 value. And then the Q is the 1 minus that. So if I use the 30% here, Q is 0.7. If I use the 60% in that other example, Q would be 0.4. And then do the math. But you'll notice that's 752, that's 632, that's a savings of, wow, 120 folks. that's a pretty significant savings. If you have to make the phone calls or talk to those students, you're pretty happy that you have to call 120 fewer students and find out whether they have a tattoo or not. So that's the idea behind the determining the sample size. They are formula problems. Again, I try to stay away from formulas. For confidence intervals, forget the formulas. You're not going to use them. I'm not going to ask you to do that. I'm going to ask you to do interpretation. I'm going to ask you about assumptions. But when it comes to the determining the sample size, those are only formula problems. So try them. Make sure you can do a couple. And I always give a practice exam that's got a couple of good examples on it, and there's plenty of homework problems, as I mentioned earlier, that have really good examples of working with these formulas. So give them a shot and see what you think. And until next time, good luck.